So let's start. This is joint work with Edgardo Stockmeyer and our student Danko from Chile, Julien Rico, who was in Munich and is moving to France. And also it started from a lot of discussions with Sébastien Breteau and Nam from Metz and Munich as well. So actually, it's about the nonlinear Dirac equation, but I think it's instructive to start actually with what happens in Schrödinger, to look a bit about at analogous questions, and then move to the model we're actually interested in and where we have new results, and show you some things that are that we were able to do, and a lot of things that we are not yet able to do. So there are a lot of open questions as well at the end. So the nonlinear Schrödinger equation is displayed here on the slide. So on the left-hand side, we have a psi, which would be complex valued. Everything will be in one time and one space dimension. So on the left-hand side, we have the time derivative with an I. And on the right-hand side, we have like what in quantum mechanics one would call kinetic energy, so minus Laplace. And then you have something that would be like an electrostatic potential. So this psi creates its own electric field or whatever physical interpretation you want to give it. That goes into this F. This F is positive, monotone increasing, and sufficiently regular. And so it creates its own potential well. So this is like a kind of intuition why this kind of equation should have like some kind of confined states or what's called standing wave solutions or solitary wave solutions. And these solutions have an harmonic time dependence here, and then some space dependence. And you can, since this is in one dimension, so this space dependent part is the one that satisfies an elliptic nonlinear equation. Maybe unfortunately, in one dimension, this equation is really easy. And you can easily see that there is a unique solution up to translations in space, the U1 symmetry, so multiplying by a phase. And so throughout the rest, phi 0 will be the solution chosen to be real, positive. Actually, it will be strictly positive. And even, so you can center it since you have translation invariance, so you can choose it to be even. That's about this equation. And then so these solitary waves do exist. And then the next question is to ask about how physically relevant they are. Are they stable or unstable? And there are many ways to make this question mathematically precise. But if for a few more minutes we look at it with physicists' eyes, then you can just say, okay, well, we take something that's the solitary wave solution plus something that would be a perturbation. And since this is nonlinear and we want to know something, we take a Taylor expansion and we keep only the linear terms. So that's something you can do more or less because okay, psi can be complex valued, and P as well. And if you expand, then you will have terms that are linear in P and linear in P conjugate, or whichever way you want to organize the computation. So in order to have a nice problem, the usual thing to do is to organize the real part of P and a part that is purely real and a part that is purely imaginary in a vector. And then after plugging in this ansatz in the equation, using that phi 0 solves the equation, and then throwing away everything that's at least quadratic in P, you can write it as an evolution equation with the IDT here, and then some operator H here acting on this components. And this operator are two blocks of diagonal blocks that have the first term just a Laplacian minus omega. Omega is always negative, so this is actually plus something. And you subtract the potential well created by phi 0, which is often called the ground state. And L plus is this notation of calling them L minus and L plus is the historical usual notation, but L plus is actually below L minus, because it's L minus minus 2 times this quantity, and phi 0 was positive and the F was monotone increasing. So this is actually a positive quantity. So this is what you get. And then still with physicist eyes, you say, okay, fine, I have an operator here. If this has a real spectrum, then since I have the eye here, I will have only oscillating modes. And then if this one has spectrum on the positive imaginary axis, I will have exponentially growing modes. And these are the ones that I will call unstable. So spectral stability, this notion corresponds to the spectrum of this linearized operator, being away from the half plane in the complex plane that is that has positive imaginary part. So that's the notion we are interested in. This H has spectrum there probably, because these blocks are different, so it's not a self-adjoint operator, so there's no direct way to say it. And what you can also see with a little bit more inspection is that if it has some eigenvalues, then the complex conjugate and minus the complex conjugate and minus the number are also eigenvalues. So it doesn't matter if you have the positive imaginary part or negative imaginary part. As soon as H has eigenvalues which are not real, then you will have spectral instability. So we are interested in this question. And there are a few things that you can see quite easily. Where do I zoom in here? Okay. I don't know how to zoom in, so I hope you can read it. So a first thing that you can look at these operators, L plus and L minus, their essential spectrum is just a thing that comes from minus the Laplacian minus omega, which was negative. So it's something that starts here at minus omega and is above 0. And then L plus was it has the same essential spectrum, because the difference is only something that is decaying. So the spectrum of H, if we then group them in this block form, you will have plus the essential spectrum and minus the essential spectrum. So you will have something that goes from minus infinity to omega, and from minus omega to plus infinity. And also you can find quite easily this set of equations. The ground state is an eigenfunction of the operator L minus associated to the eigenvalue 0. This is just by rewriting the equation, the nonlinear elliptic equation is exactly this. And then if you think about translation invariance, you can find out that phi 0 prime is an eigenvalue of L plus associated to 0. So you have these guys at 0. And then also, okay, so you have, for L plus, you have this at 0 here. And for L minus, you also have one at 0. Since phi 0 is strictly positive, it doesn't change sign. It corresponds by a typical oscillation argument. It corresponds to the ground state. It is the lowest eigenvalue of L minus. And so this L minus has its ground state at 0, so it's positive semi-definite, and it's actually positive definite away from if you are orthogonal to this ground state. And then L plus has a 0 eigenvalue with this eigenfunction, which if phi 0 is like the typical shape of a single bump, has a single 0. So by the same type of oscillation argument, L plus actually has one more negative eigenvalue, precisely one. This is a very one-dimensional part of the argument. Other parts are not really dependent on the dimension, but this one does. So we can learn a lot about the spectrum of L plus and L minus. And then there could be some eigenvalues here, or even resonances or things, but they don't really matter for the spectral thing at all. And then another thing that you can see is that if we have an eigenvalue of of H, the operator that was not self-adjoint, that has these blocks, then actually its square is real. That's another way to say that it's either on the real axis or on the imaginary axis. And to see this, you just write out what it means to be an eigenvalue of this. You have to check that this phi1 will be orthogonal to the ground state, but this is taking inner products in this equation. So that's you can actually invert L minus when acting on phi1. And then if you go through the computation, you find that this is equal to, I don't remember if it's phi1 or phi2, but I think it's phi1. Phi1 L plus phi1. What's important is to check that this is an expectation value with a self-adjoint operator. So this is a real number. This number is real and never zero, because orthogonal to the ground state is positive definite. So this is not zero. So the only way to this z squared should be also a real number. So a priori, the eigenvalues could be anywhere, but a posteriori, we see that they are only on the axis. And then there was a nice small argument that is apparently based on work by Zakharov. I don't really know the original references, but it's normally called the Vakitov-Kolokolov criterion. Especially in the more applied literature, that says that if you take a look at these ground states as a function of omega, and you take their L2 norm, which is sometimes called the charge. So you have a function of omega. If this function is nice enough to allow for a derivative, and this derivative is negative, then there are no imaginary eigenvalues. So then all the eigenvalues are on the real axis, and the whole problem of spectral stability is solved. So this is something that's very, well, if you have explicit formula, you can check it. And if not, you can find this phi zero and plot it. So it's a very convenient way to check spectral stability. And it's, I still find it very remarkable that the same condition, so a single negative eigenvalue of L plus, and this condition on the derivative is the one that appears in the famous papers of the 80s by Grilakis, Shatta, and Strauss, and also implies a way stronger notion of nonlinear stability, which is orbital stability, which says that if I start out close to a ground state, I have to plug in my computer, sorry. Okay. Sorry, I forgot this. If you start at very close to a ground state, then you will stay close, maybe not to the exact evolution of e to the minus it omega, but close to the ground state times some phase, some complex number of modulus 1. Okay, so this summarizes, I think I'm talking very fast, but I hope it was okay. It summarizes well-known since a long time things for the Schrödinger equation. And it's a bit to guide our intuition for what we would really love to prove for this nonlinear Dirac equation. So now, this is the equation where actually the talk is about. So it's again an evolution equation, but now for C2 valued spinor, they're usually called psi, so something with two components. On the left-hand side, IDT, and on the right-hand side, so the kinetic energy is now the Dirac operator with mass m, which is here. So you can you have one derivative and a mass, and you can pick your favorite Pauli matrices. There are different conventions in the literature, but the important thing to call this a Soler model or a generalized Soler or something like that is that the matrix that goes with the mass is the same matrix as the one that goes here inside the nonlinearity. So all of this nonlinearity, you can see it as a first variation of, which would be f, the primitive of this small f of psi sigma 3 psi. So this thing describes something what let's call it a spinor because it's or a fermion because it's described by a Dirac equation. that creates like a well in its own. It modifies its own mass. It modifies the mass that it sees. And a mass well, a modification of the mass locally, lowering the mass locally is something good to confine things that are described by Dirac. There is a physical phenomenon called Klein tunneling that says that in electrostatic potential is not good to confine Dirac particles, but a mass potential with the sigma 3 here is. So if you believe that intuition and otherwise, you can also quite easily just look at the equation. Then you can convince yourself that this is a good candidate to have this kind of solitary wave solutions. So in one dimension, existence is very easy. And here, just to give you some idea what they look like. So for all omegas between 0 and n, you have this kind of solutions. This one is for the cubic equation. So the nonlinearity is order 3. And again, you can choose them such that the first component, which is plotted here, is even. The second component is odd. Both are real. And the first component, yeah, so it's even and positive. That was the word that was missing. And an interesting feature about this is that they correspond so in some sense to ground states, but in other senses they have a especially okay. These are different values of omega. So for small omega, it's very flat and very similar to the Schrödinger. Sorry, for omega close to m, this is below. It's very similar to the Schrödinger case. Omega goes to m is actually called the non-relativistic limit, and you can show that then in that case, it in a suitable sense, things after some rescaling and things like that, things begin to look a lot like the nonlinear Schrödinger equation with the same f. And in the other limit, when omega goes to 0, things start to look weird and very peaked. But actually, that's quite interesting that these ground states, they don't have their maximum, especially if you sum v squared plus u squared. They don't have their maximum at the origin at all. They have like a 2-bump type profile. So as I said, existence was not an issue in one dimension. About stability, for the sake of time, I would summarize by almost nothing is known. So it was a wide open question. So that's why we turned our attention to the weakest possible notion, which would be spectral stability. And here are a few things you can do. So first thing you can do is to linearize the equation in exactly the same way, only to keep in mind that our spinors already had 2 components. So now if we split again in real part and imaginary part, we will have 4 components in total. But if you look at it, it will have blocks that are very similar. I call them L0 here, which is this one, at the Dirac operator. You subtract the frequency they oscillate, and then you have the mass. So the components of phi 0, they're traditionally called V and U. So you subtract this quantity times sigma 3. And then the below left block is the same, only that you subtract another matrix now, because this is a 2x2 block that has this shape, and it's positive semi-definite. So this is very similar. You also have the same eigenvalues associated to U1 symmetry and translations. And then you have another one by some kind of spinor magic, which is both of L0 and L0 minus 2Q. Here is a phi 0 missing, which is sigma 1 times phi 0. So associated to minus 2 omega. So here it's written. So the free Dirac operator has essential spectrum all the way from minus infinity to minus m, and then from m to plus infinity. But here you subtract omega, so we go 2 minus and minus omega. And then we have the 0 and this minus 2 omega eigenvalues. If you look at the block, the H operator that's not self-adjoint, then its essential spectrum is here. And we know that it has also a double eigenvalue 0 and minus 2 omega and plus 2 omega as eigenvalues. That was the part that was well known and pretty straightforward to do. Unfortunately, there is no argument to exclude a priori eigenvalues away from the axis in the complex plane, because we have this kind of identity. Sorry, L2 was not defined, but it's what's here, because it's L0 and then 2 times this, minus 2 times this thing. So you get the same kind of identity, but you cannot conclude anything because this quantity could be very well 0, because L0 is not sign definite in any sense, because well, its essential spectrum goes all the way to minus infinity. So we don't know where the eigenvalues are. And so, but still we can say a few things. So that's what I'm going into now. The first thing is it has a very simple proof in one dimension, but it identifies in some sense a ground state, because we know that the spectrum of L0 looks like this. It has these eigenvalues. And then what we say is that they're known in between 0 and minus 2 omega. For Schrödinger, you say, okay, phi 0 is the ground state, and they're no all the way below, all the way to minus infinity. We have no way to say that, but at least they're known in this interval. And then for L2, at least for the case of power nonlinearity, so F is a positive power, there's exactly one eigenvalue here, somewhere in between the ones that we know. So this is a first result, and it says in some sense that phi 0, if you look at this, the spectra of these block operators, behaves very similar to a ground state. So that's a good thing. The next result concerns this Vakitov-Kolokov condition on this derivative. One thing is to show that it exists. We do that. And then instead of just looking at the operator we are given with the block, we look at a whole family of operators, but which are very simple modifications. The operator I showed you just a while ago had L0 and then L0 minus 2 times this matrix Q. And then I just define L mu to be L0 times minus mu times Q. So this is an analytic operator family. And the nice thing is when mu equals 0, then you have L0 and L0. So then you know that this is a self-adjoint operator and its spectrum is all on the real axis. So the point of view is to look at how this, well, the essential spectrum will always be the same, and the eigenvalues will be on branches in the complex plane. So we look at how they can behave. And if you have these two conditions, a single eigenvalue, which we have already seen that is satisfied, and this one, which is easy to check, then there are no eigenvalue branches that pass through 0. So in particular, they're known the two things. These are straight lines that start somewhere on the real axis. They collide at the origin, and then they go into the complex plane. Because this condition forbids, in some sense, that branches pass through 0. So this would be nice. We would say, okay, we don't know what happens around in the complex plane, but at least there are no branches there. But there could, a priori, if you look at this just like that, there could still be eigenvalues that appear, I don't know, somewhere in between, and then do all kind of crazy things. And then exactly at mu equal 2, they arrive to the imaginary axis. But luckily for some values of the parameter, we can do other things. We can do really bounds. This part is more like linear algebra and matrices and things like that, and multiplicities. And this one is just if Z is an eigenvalue that is not on any of the x's. C squared is not real. And if this perturbation part Q, depending on omega, is sufficiently small, quantitatively sufficiently small, then its real part, the real part of the eigenvalue should be squared, should be positive. So that's means that it cannot be anywhere here or here or here or here. So then the only way to live in the imaginary axis for an eigenvalue of h is really this passing through zero. So I will finish with this picture, combining these two IDs. So this bluish region shows where the derivative, oh, sorry, other way around. This bluish region shows where the bound holds. So no eigenvalues can go to the imaginary axis unless they pass through zero. And the green region shows, okay, in the plane omega, frequencies that go from 0 to m, and p, the powers of the power nonlinearities. As a function of these guys, this green region is where the derivative of phi 0 squared is non-positive. And so no eigenvalue branches can pass through zero. So in the intersection, the darkest region here, there are no eigenvalues on the axis in the complex plane. Unfortunately, this is not a complete answer to the question, but we were very happy to make some progress on the problem at last anyway. So I'll leave this slide here to look at the open questions. And thank you very much for the nice session and for the opportunity to talk here.
Thanks a lot.